This is Mrs. Milton. Today's two videos are for section 1.3. In the book, it's officially called Applications and Other Sequences. So basically, applications means we're going to do a couple story problems, and then the other sequence we're going to work on is something that's called a shifted geometric. So the first video, I'll kind of introduce some of the new vocabulary to you, and then the second video, we'll jump into a couple of examples together. All right, so a review from what we've been working on so far this chapter is we've been living in this world of recursive formulas where you take one step at a time, the previous information to get new information, and you can remember that recursive formulas have two parts. Remember, an arithmetic recursive formula, you need something to start with, and then you need a rule where you take the previous term and then you add a common difference. Maybe you subtract 3 each time or add 7 each time. Where a geometric sequence, maybe you start with u sub 1, u sub 0, you need somewhere to start, and then you always take the previous term and multiply it by some common ratio. Maybe you multiply by 3 each time to get the next term, or multiply by 1/2 each time to get the next term. And then a nice thing that yesterday we talked about, that there's a shortcut for geometric formulas. You can just jump right in to find the term you want. Is you take that beginning term, multiply it by the ratio to however many times you need. So it could look just like that. There are no shortcuts for arithmetic at this point in time. We'll get to one later, but we don't have one yet. Today we're going to talk about a shifted geometric, where basically what's happening there is when it's a geometric, you multiply by something, but then you add or subtract something at the end. And we'll get into that in the second video. It'll become pretty clear for you. The other thing we're going to talk about today is this idea of a long run value. And you know what? I'm going to back up a little bit. This u sub 1 needs to be u sub 0. We need that starting point. We'll review that, not to worry. We're going to talk about a long run value, and basically a long run value, it gives us a shortcut. It basically tells us if we start with the first term, maybe things will level off, and we want to know what happens in the 100th term, because maybe we're in a geometric sequence where it levels off. So we're going to talk about, and it wants to know what's happening in the long run. What happens, what's the value when we've started leveling off? That'll be the long run value, and we'll talk about that right now. All right, this is a lot of words. I don't expect you to write hardly any of it down, but I am going to read it and would love for you to follow along. It says long run value. Many real world changes do not exactly have equal distances or equal ratios, like the D or the R. Can a tree continue to grow larger year after year? Can people continue to build taller buildings, run faster, jump higher? Or is there a limit? Does it kind of eventually level off on how tall a certain tree grows or how high someone can jump? I know the pole vault world record has held for probably over 20 years now, maybe even 30. So for example, the temperature of hot cocoa, I'm going to use this example of hot cocoa a lot. You'll get used to it. The temperature of hot cocoa as it cools, taken at 1 minute intervals, produces a sequence that approaches the temperature of the room. In the long run, the hot cocoa will be at room temperature. This amount is called a limit. Mathematically, we say that the sequence of numbers associated with the system approaches that limit. Being able to predict limits is very important for analyzing real-world situations, and the long-run value helps you estimate limits. So you think of long-run and limits as the same thing. This idea of limits comes up all the time in calculus. You will be calculating limits constantly, so getting a little exposure now never hurts. But let's go back to that hot cocoa example a little bit. If we look at the first quadrant here, we're going to have temperature be on the y-axis and time be on the x-axis. And let's say, so you heat up your hot cocoa, it comes out of the microwave, and it's whatever the temperature. Then every minute, the hot cocoa sitting on the counter is going to cool off, and eventually it's going to level out. And just like we read above, like what temperature is it going to level out at? It's going to level out at whatever the temperature your room is. So maybe 70 degrees, maybe you keep a cooler house or a warmer house, but we'll say it would level off at 70 degrees. So in the long run, the temperature of the cocoa is 70 degrees, or you could say the limit is 70 degrees as well. Okay, so that is the idea of long run value. And let's talk about it just a little bit more. A long run value, here's U sub n right here, that's the current term. What would be true about U sub n minus 1, that value right before it? So if you've waited 45 minutes with the cocoa on the counter, what's the temperature at 45 minutes versus the temperature at 44 minutes? Is there going to be the difference? The idea is that the long run value is that they're the same. U sub n equals U sub n minus 1. They'll both be about 70 degrees in this case. So what we're going to do when we calculate long run value is we'll treat it that U sub n, the current term, and U sub n minus 1 are the same. So if I call U sub n x, I'd call U sub n x, U sub n minus 1 equals to x as well. I'd call it the same thing. So let's try an example for long run value. Looking at here, you might be asked to find the long run value for a sequence. It looks like I have the 0th term before anything changes to be 48, and then it looks like you'll plug that in, so that 48 will get plugged in to U sub n minus 1. We'll multiply it by a 0.75 and then add 25 to it. You've never seen a rule like this because right here, that looks like geometric, but right here looks like arithmetic. That is, we'll get into it later, but that is a shifted geometric where the previous term gets multiplied by something and then something gets added or subtracted on the end. So a shifted geometric you think of as a combo arithmetic geometric. But let's go ahead, let's find this long run value. Well, what you do, it's actually quite simple. You could plug in the 0th term is 48 and plug in to find the first, the second, the third, but you will have to go for a really long time to get where they start leveling off, where whatever the value is will stay the same, and that might take a long time, and who wants to do that much? So what you can do to calculate that long run value is take this part of your recursive equation, the rule, and didn't we say we just talked about how U sub n and U sub n minus 1 are the same. So let's rewrite them, calling them both x, like we talked about. Whoa, hello. Smartboard was doing so well. We have our first incident. Let me scooch it up to see if we can clean that up a little bit. See if it works better up here. 5, and then here was the x, that U sub n minus 1 plus 25. So all I did was rewrite the second part of my recursive equation where U sub n and U sub n minus 1 are both x. Now, all we have to do is solve for x. Oh man, let's bring it down here. I'll try that. So I'm subtracting 0.75x from both sides. So this is like 1 here. So I've got a 0.25x equals 25. Divide both sides by 0.25. So it looks like in the long run, x is going to be right around 100. So it starts at 48, and in the long run, it's going to get to be where these are basically the same as 100. So it looks like this shifted geometric is a shifted geometric growth because it starts at 48 and grows to about 100. So when it says find the long run value, you would say it's 100. All right, we have one more video to go. I'm going to show you 2 examples in that one. Thanks for sticking with me in this one.
See you in a minute.